Okay, in this video I'm going to talk about Fourier series. So we are going to discover more about Fourier series and the function of Fourier series function, and we are going to explore more about the importance of Fourier series based on the examples that we are going to take. Okay, let's jump into the introduction directly. Okay, let's start with what is the meaning of Fourier series in general. So a Fourier series is a representation of a function. So first of all, it is representation of a function, any function. So if you have any function, and you want to represent it using certain or you want to represent it in another way using specific known functions like sine and cosine, then we can use Fourier series. Okay, so a Fourier series is a representation of a function, any function, as I said, as a series. So this is important also. Series of constant multiples of sine and or cosine functions of different frequencies. That's the issue. That's the main idea of this Fourier series. We are going to simplify any kind of function to a series of sine and cosine, as you can see here. So as you can see here in this, let's assume that we have this function. As you can see, this function actually can be represented by, as you can see here, different as the summation of different series of sine and cosine functions. These are sine and cosine function, as we have mentioned here, okay, of different frequencies. The frequency of each one is going to be different than the other. Okay, so that's the point. This is the main issue. The frequency, I can say something, this is the frequency of one function, for example. Other function can be something like this. The frequency is totally different. Okay, so we are going to have the frequency here is very high and the frequency here is low. So we are going to bring these functions together, and we are going to say that the summation of these sine and cosine, okay, is going to give us the original function. And this is actually very useful in many applications, as we are going to see. Okay, now let's go to the mathematical part of Fourier series function. Okay. Now let's start with the decomposition of the function into a sum of terms. This idea which we were talking about, that we are going to decompose any function f of x, we are going to decompose it to several functions that is related to sine and cosine and so on, right? So the Fourier series of a function, we can define it like this. Let f of x be defined on this interval, which is minus L to L. So we are talking about interval from minus L to L, for example. Okay. We want any function, okay, any function here. Okay. We want to choose numbers. We want to choose numbers like a node, a1, a2, and other types of numbers, b1, b2, and until bn, for example, so that what? This function that we have started, which is defined on this interval, is going to be represented by these coefficients or these numbers that we have selected or that we are trying to obtain, multiplied by the cosine and sine functions. So now we found that in this equation, this f of x can be represented by a node. This is the first thing here, okay, and then we are going to find after that ak, where k takes the values from k equal to 1 to infinity, times cosine. So this is the coefficient that is going to be multiplied by the cosine function, and then we are going to find bk, where k is taking, as we said, from 1 to infinity. This is starting from b1, b2, and so on, okay, times sine function. So we are having here the cosine function and sine function. the cosine function is multiplied by ak, this is cosine something, plus the bk is multiplied by sine something, okay? And then there is another term that is relating or having a node in the beginning. This is what we are decomposing the original function for. So our main interest now, let's clear everything, that we want to know, okay? So we can say this is going to be, this is a decomposition of the function into a sum of terms, each representing the influence of a different fundamental frequency on the behavior of the function. So each one is giving us a frequency, okay? So because we're having here from k equal 1 to infinite, so we have like one term and another term and another term, and this is also going to give us another like different terms. So based on this summation, we're going to put the influence of each term based on its frequency on the original or the function that we are seeking for, okay? So again, in order to remind what we want to know a node, ak, and bk. So we want to know these coefficients, okay? B, a node, a1, a2, and b1, b2, b3, okay? So remember well that we need these coefficients to represent this function on this interval, okay? As I said, this is any interval that we have from minus L to L, then we can have any kind of function here. We want to describe it or represent it by using Fourier series, by using sine and cosine. Okay. Now let's go to the how to obtain. So now we understood from the previous slide, we understood that we want a node, ak, and bk. These are the most important thing for us. Okay. The other remaining parts, it is known for us, sine and cosine. So now let's go to a node. Let's go to a node. To determine a node, what we are going to do here, we are going to integrate equation 13.1, which is this equation that we already have defined in the previous slide. Integrate equation 13.1 term by term to get, so we're going to use term by term integration to get a node, to know how we're going to obtain a node, for example. I'm going to take only how we can obtain a node, and then from this you're going to have an idea of obtaining the coefficients. Then the remaining ak and bk is going to be like some routine integrations, you can obtain them easily. So I'm going to set or put them directly. Okay, only I'm going to show to you here how we can obtain a node. So now the left hand side of this equation is going to be f of x. So we are going to integrate it from minus L to L, okay, dx. And then it equals to, the first term is half integration of minus L to L, a node dx, plus the second term here is the summation of these functions that is containing cosine and sine. And there is parentheses here. Between parentheses, we are going to use ak multiplied by the integration from minus L to L to cosine k pi x over L. This is common. And then dx plus bk, the integration from minus L to L, sine k pi x over L dx. This is common, right? If you are going to look to this integration, look to this integration. It is a cosine function from minus L to L. What is the integration of it without thinking too much? Okay, so yes, that's right. It is going to be 0, right? Because in general, if we have sine or cosine or whatever, if we have something like this, and we are going to integrate, so this will vanish, this will cancel, the positive part will cancel the negative part, for example, and so on and so forth. So this would happen for cosine and sine as well, from the limited integration from minus L to L. So this is going to be 0, and this part also going to be 0. This means that these two terms are going to cancel out, and we are going to find that this term, that is the only term remaining for us, right? So we're going to have half a node 2L after making the integration of a node. This is a constant, right? So we have here 2L, And then we can say that after rearrangement and canceling 2 and so on, so we are going to find that it equals to a node L, means that a node times pi, because already we have our integration or what we are using for the limits, which is L. Okay, this is going to be the from minus pi to pi, corresponding to minus L to L. Okay, now this is because all of the integrals in the summation are 0. Then we are going to find that a node okay, is going to equal, let me clear everything. So we're going to find that a node equals to 1 over L, 1 over L, okay, the integration of from minus L to L, f of x dx, right? Didn't do anything. Just we looked again to this and equated to the original one, and we found that we are not going to do anything. Just we are going to say that the first coefficient here is going to be a node equals to 1 over L, the limit that we are going to have, okay, from minus L to L, for example, and then the function is going to be integrated over this interval, which is from minus L to L. So this means that, physically means that a node is the integration of the function from minus L to L, the limits of the interval, divided by L. This is the physical meaning of a node. The physical meaning of a node. Okay. Now let's go and let's obtain the remaining coefficients. Remember that we want to obtain AK and BK here. We can obtain the other coefficients in the equation. This is the equation here. Already we obtained a node. We know how to obtain it. And in a similar fashion, okay, we are going to obtain these two coefficients. Okay, so we found that an is going to be 1 over L, the integration of from the limits minus L to L over the interval, f of x, the function that we are using, times cosine n pi x over L dx. Okay, this is how an is going to be defined. And remember that we are using n here, so this is an integer that is starting with 0, 1, 2, 3, and 4. Okay, so this is an. For bn, it is going to be in a similar fashion, very similar to this. 1 over L, the integration from minus L to L, f of x sine n pi x over L dx for n equal to 1, 2, 3, and so on. Okay, so we are having now all the coefficients, okay, based on this. We have here 0, here we do not have, we start here from 1 directly. Okay, so remember this. So these numbers a node and an and bn are called the Fourier coefficients of the function f on the interval minus L to L. When these numbers are used, the series 13.1, this is what we call it, the series here, is called Fourier series of the function f on the interval minus L to L. Okay, so this is considered to be, as I said, what? The Fourier series. The Fourier series that we are going to use on, or the Fourier series for this specific function. Okay, I think now we are ready to have a quick example that is going to illustrate for us the main idea. Okay, now let's assume that we have a function f of x equals to x squared minus x to the power 2. X minus x squared, okay? X minus x raised to the power 2. Okay. For this is the interval that we have. So this means that we have the interval here, minus L, which is minus pi, and the other limit is L. Okay, so we have minus L and L. L equals to pi. Okay, okay. Here L equals to pi, as we said. Okay. Compute, first of all, we need to compute the original coefficients. So remember, we want a node, we want AK, we want BK, or a node and an and bn, right? Okay, so now a node is not a big deal because already we have done it before. A node, do you remember this equation? that a node equal to 1 over L, the integration from minus L to L f of x dx. So we are going to make the integration from 1 over pi, from minus pi to pi, x minus x squared dx, right? So this is a very simple integration, limited integration, okay? And then we can obtain, this is the result, or this is the value of a node. It is minus 2/3 pi squared. It's a number. Okay. Now let's go to or jump to the next coefficient, which is an. Again, we are talking about an, which is going to be here. Okay? That is the coefficient, or the number that is going to be multiplying the cosine function. Okay, so an, as we have mentioned, it equals to 1 over pi. Remember, 1 over L. Let's go back here. 1 over L minus L to L, integration over minus L to L, f of x cosine n pi x over L. So this means 1 over L, or 1 over pi, from minus pi to pi, x minus x squared. This is the function that we have. This is the function, right? This is f of x that we have. Cosine n pi x over L, okay, which is going to be cosine n x, okay, n x, because we are having here, so okay, so we have here, okay, so we have here, it is nx, because we have n, this is actually n pi x over L, right? But L, it equals to pi, so it cancels out with pi, so the remaining is nx. Okay, and in this case we are going to have, this is two functions are multiplied by one another, the integration of two functions. Do you remember the integration by parts? So recall integration by parts and remember and recall your calculus class. So anyway, after making the integration, you're going to find this big like fraction that is going to have the denominator and the numerator, as you can see here. This is the integration by parts, if you remember. Okay, so you're going to find that you have 4 sine n pi minus 4n pi cosine n pi minus 2n squared pi squared sine n pi over n cubed pi. Okay, without thinking too much, sine n pi is always exactly 0. So we are having these two terms, they are going to cancel out. So sine n pi equal to 0. So we're going to end up with the remaining term at the middle term, which is going to be 4n pi cosine n pi over n cubed pi. Okay, so this means that we are going to say we have minus 4 over n squared cosine n pi equals to minus 4 over n squared minus 1 n, and this is common because n pi, okay, cosine n pi, it is always going to be exactly, it is going to be minus 1, and in this case it is based on n. How many times? If we are going to multiply it twice, for example, then it is going to return to be 1, right? So if we're going to raise it to the power n, then it is right. It represents this, because if you remember this like little circle here, that is, we have 0 here and we have pi here. So whenever we are talking about cosine, so this is like, as we said, this is minus 1, for example. Okay, and this is 1. So if it's 1 pi, then it is going to be minus 1 cosine pi. If we have like 2 pi, for example, in this case, we're going to have it like positive 1, and so on. So this means that cosine n pi, it is going to be minus 1 raised to the power n. It represents right the cosine with with n pi, where n is an integer. Okay, and we have minus here, so this is going to be like raised here again. So we are going to say we have 4 minus 1 raised to the power n plus 1 over n squared, as it is. So we didn't do anything, just rearrange it. If we clear everything, this means that this is going to be our an, right? This is going to be our an. This is going to be our first coefficient in Fourier series. Okay. Okay, so now remember that for these abbreviations we have used facts that sine n pi equal to 0, of course you understand this, and cosine n pi equal to minus 1 raised to the power n if n is an integer. Okay. Okay, now let's go to the Pn. Okay, it is Bn, the other coefficient that is multiplied by cosine, right? So we're going to make the integration 1 over L, which is pi, from minus L to L, minus pi to pi, x squared minus x minus x squared, sine n pi x over L, and it goes to nx only. This means that we are going to find, also integration by parts, and we are going to find that we're going to end up with this fraction here. 2 sine n pi minus 2n pi cosine n pi over pi n squared. Remember that sine n pi is going to be 0, as we said before. So we're going to remain with this term. After rearranging this term, we have a minus here and cosine n pi, so we are going to raise it. Cosine n pi, it is going to be minus n. This is, sorry, minus 1 raised to the power n, and then multiplied by this minus again, so it is going to be n plus 1. So we're going to end up with 2 times minus 1 raised to the power n plus 1 over n. Okay, now let's go to the final result here, how we are going to see our function. Okay, how we are going to see our function. Clear everything? So our function, okay, our function, which is going to be, as we said, it is x minus x squared. This is our main function. This is f of x, right? It can be represented like this. Half times a node, which is, this is the first term, which is half times a node. Okay. And second, it is the summation of n equal to 1 to infinity, ak, which is going to be second term, which is this term, as we said, this is an, right, times cosine n pi x over L, which is nx, and then plus another term, which is going to be exactly, this is our term here, okay, which is bn times sine nx. Okay, this is the representation of this function. This is the representation of this function using Fourier series coefficient, and or using Fourier series function. Okay, this is how it looks. So the Fourier series of f of x, which equals to x minus x squared on the interval minus pi to pi, this is the function. Okay, this is the function. It consists of what exactly? Some cosines plus some sines multiplied by numbers, and there is a constant outside. That's it. This is how we are going to work on our function. Okay, it is some constant here and another constant multiplied by cosine and another constant multiplied by sine. These are the 3 components that is going to work for us for this function. Okay. Okay, thank you, and next time I'm going to talk about Fourier series convergence. And for this video, thank you for listening, and see you next video.